What if the most important car part isn't an engine at all? No pistons firing, no fuel igniting, no exhaust roaring behind you, just silent force, delivered instantly. An electric vehicle is not a traditional car with a different fuel tank. It's a real-time energy system on wheels where chemistry, software, power electronics, and magnetism move in perfect sync. And once you see what's happening under the body, one thing becomes obvious. EV speed is not magic. It's engineering precision, the secret physics of EVs, why they're faster than you think. 1. The heart under your feet, the battery pack. Forget the old mental picture of engine in front, fuel tank in back. In most EVs, the biggest source of power sits flat under the cabin floor, the battery pack. Inside that pack are thousands of rechargeable cells, grouped into modules, managed as one coordinated energy unit. A single cell can't move a vehicle, but thousands, connected intelligently, can launch 2 tons of metal with shocking urgency. At the chemistry level, most EV packs use lithium-ion systems. During charging, electrical energy is stored chemically. During driving, that chemical potential is released as electrical power. But the battery does more than store energy. Its position low and centered drops the vehicle's center of gravity. That means better stability in corners, less body roll, and a more planted feel at speed. So the battery isn't just the fuel source, it's also a structural and dynamic advantage. 2. The translator, DC to AC in milliseconds. The battery delivers DC power, direct current, but many high-performance EV motors are driven by controlled AC waveforms. That conversion happens in one of the most important components in the entire car, the inverter. Think of the inverter as an ultra-fast electronic switchboard. It takes raw battery output and reshapes it into precisely timed electrical waves that command the motor. Press the accelerator lightly, the inverter sends a measured, efficient flow. Press hard, it immediately increases current and waveform demand for aggressive torque. No gear hunting, no combustion delay, no waiting for revs to climb. That direct electrical command is a key reason EVs feel awake the moment you touch the pedal. 3. The muscle. Magnetic force becomes motion. Gas cars depend on controlled explosions. EVs depend on controlled electromagnetic fields. Inside the motor, magnetic fields are created, rotated, and synchronized with incredible precision. Those fields push and pull internal rotating components, generating torque at the shaft. The shaft turns the drivetrain. The drivetrain turns the wheels. That's the chain. Electricity, magnetism, rotation, motion. Here's the headline. Electric motors can deliver near maximum torque from 0 RPM. That is why EV launches feel so immediate. The pulling force is available now, not after an engine climbs into a power band. Many EVs also use single-speed transmissions, fewer moving parts, fewer frictional transitions, smoother acceleration curve. You're feeling the benefit of simplified mechanics paired with advanced control electronics. 4. The energy refund, regenerative braking. In a conventional car, braking usually dumps motion energy as heat. In an EV, part of that motion can be recovered. When you lift off the accelerator or apply braking, the motor can switch roles and act as a generator. Instead of consuming electrical energy, it produces it. That captured energy flows back to the battery. This is regenerative braking. In traffic, where you constantly slow and speed up, regen can significantly improve overall efficiency. Every deceleration becomes an opportunity to reclaim energy that would otherwise be lost. It's not infinite energy, it's intelligent recovery. A tiny refund, repeated thousands of times across the life of the car. 5. Grid to road. How charging actually works. Charging is not one size fits all. Different charging methods change time, convenience, and daily ownership experience. Level 1 charging uses a standard household outlet, slow but useful for light daily mileage and overnight replenishment. Level 2 charging uses dedicated higher power AC equipment at homes, offices, or public locations, much faster for routine use. DC fast charging supplies high-power DC directly, enabling rapid range additions on long trips. With AC charging, the car's onboard charger converts incoming AC to DC for the battery. With DC fast charging, much of that conversion happens at the station, allowing greater power throughput. Throughout all charging modes, the vehicle continuously monitors voltage, current, temperature, and cell behavior to protect battery health and optimize charging speed safely. Six, the digital conductor, BMS plus thermal control. If the battery is the heart, the battery management system BMS is the nervous system. It monitors cell groups, balances charge distribution, enforces safety limits, and coordinates charging, discharging behavior in real time. Why is that crucial? Because batteries are temperature sensitive. Too hot, and degradation risk rises. Too cold, and performance drops. So EVs use thermal management loops, often liquid-based, to maintain stable operating conditions. Cooling and heating systems keep the pack in its optimal window for performance, charging consistency, and long-term durability. This is where the computer on wheels idea becomes real. You're not just driving a motor and battery, you're driving a constantly optimizing control platform that protects, predicts, and adapts every second. 7. Why EVs feel different and why that feeling is real. People often say EV acceleration feels unnatural. What they're noticing is the absence of traditional delay, no combustion cycle buildup, no multi-gear downshift drama, no waiting for peak torque to arrive. In an EV, command and response are tightly linked. Pedal input becomes electrical instruction. Electrical instruction becomes magnetic force. Magnetic force becomes immediate motion. That smooth, linear pull is exactly what high-efficiency force delivery feels like. And because there are generally fewer mechanically complex moving assemblies, many EV platforms also reduce certain maintenance burdens compared with combustion systems. Different trade-offs still exist: charging access, trip planning patterns, climate effects, but the core propulsion architecture is fundamentally elegant. 8. EV vs gasoline. Two energy philosophies. A gasoline car typically follows this chain: chemical fuel combustion, heat, pressure, mechanical conversion, transmission staging, wheel motion. An EV follows this chain: stored electrical energy power, electronics control, motor torque, wheel motion. Both are engineering achievements. But one path is more direct. That directness is why EVs can feel calm and brutal at the same time. Quiet cabin, explosive response. The future of mobility is not just about replacing one fuel with another. It's about redesigning how efficiently energy becomes movement. So next time an electric car slips past in near silence, remember what you're really seeing: a low-mounted energy reservoir, a millisecond precision inverter, a magnetic motor delivering instant torque, a braking system that recovers what others waste, a digital management layer orchestrating everything in real time. No drama under the hood, just disciplined physics. No myth, no hype, just modern engineering, executed cleanly. If this changed the way you see EVs, share it with someone who still calls them glorified golf carts. And in the comments, answer one question. When your next car decision comes, do you choose combustion history or electric precision? Subscribe for more hyper-clean engineering breakdowns.